Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. This topic is a little more complex than the simple mean, and it's going to be the difference between means. Well, let's use this as an example. I'm looking at the age, or the average age of my customers across gender, and I theorize that they are the same. But when I pull samples, I see they're different. A female customer's age is 60, the average male's age is 63. But through my sampling of the means, are they different enough? Do you know enough here to say that the population means are different? I'm going to have to perform a statistical test to understand that. Assume for a moment that they were both the same, that our sample size is 60 and 63, but the values that I'm looking at are well within the region of acceptance. So it's possible that I'm just seeing a difference because that's what my sample size told me, and that's not an effect I would actually see inside the population. What I need to know, of course, is that actually the mean? If the population mean, as you might see represented here, is 60 and 63, the fact that those two overlap one another still allows that region of acceptance to put me in the position of saying, is this still just a statistical anomaly, a sampling anomaly? So I used a version of this in KNIME in a prior chapter as an example. We're going to conduct a hypothesis test on the difference between two means, and that's called a two-sample t-test. And that's appropriate when the method of each sample is simple and the samples are independent of one another, and each population is at least 20 times larger than its respective sample. So the sampling distribution is approximately normal. So we will assume in my working case that these are all true. In its simplest form, this type of t-test is simply a test that's comparing the means of two different data sets to see if they are significantly different from each other. Now, another permutation of this test is called the paired two-sample test for the means. You can use this when there is a natural pairing of the observations of the samples, such as, for example, you sampled a group before and after an experiment. So you're looking at the same person and you're looking at like their pre-test scores and their post-test scores. That's a good example of when you would use something like this. Now, take a look down here at the node repository. And you can see exactly what my choices are down here. When I look and search for t-tests, you can see that the simple sample t-test was what I've done here in the prior example, when I assumed that a person had made 100. Now, the independent groups t-test is where I'm going to take two different groups and do that t-test against them. And then this is the paired t-test, where I'm going to take two groups and do their before and after tests. So KNIME supports both of these capabilities. Now, we can do this t-test with two possibilities. We can either work under the assumption that they have equal variances. So when I pull a male and female customer, I assume that their variances and distributions are equal to one another, and that the distribution is essentially the same. The second choice, of course, is to assume that the variances are unequal, and that's generally almost always going to be a safer assumption because they're generally coming from distinct places. In fact, a good rule of thumb is this. If your data comes from, if they're not related to one another via like a paired test where there's a single set of subjects before and after, with that single set of subjects, it's reasonable to assume that the variances and distribution are equal. If they come from two different samples, here's a sample of male customers and a sample of female customers independent of one another, it's far more safe to assume that they are unequal variances. What you're going to see when we look at the KNIME node is it's going to show you the result of both the unequal variance and the equal variance, and you will make a decision as to which one you're going to use. So this time our hypothesis table is slightly different. Instead of just looking for a single value, what I'm theorizing here is I'm going to make each statement about the hypothesized difference between one mean and the other. So, for example, I'm going to say the hypothesized difference, let's say I'm going to assume it's 0. I'm going to say then the average of 1 minus the average of 2 is going to be equal to 0. And that's my null hypothesis. And if it's not equal to 0, it could be greater than or less than, so this again would be a two-tailed test. But it could be, we could say that it's greater than or equal to a value or less than or equal to a value. Just like the last time, that would make this a one-tailed test. So just like the prior example in the prior chapter, with a two-tailed test, when we see this, because the extreme value can be on either side of the distribution, it's a two-tailed test, and either extreme value would cause me to reject the null hypothesis. With one-tailed tests, the extreme value would have to be on one side of the distribution or the other for me to reject the null hypothesis. And another much easier way of reading it actually might be this, that my null hypothesis is that the mean of 1 is equal to the mean of 2, and that the mean of 1, my alternate, is not equal to the mean of 2. Both of those would yield me a two-tailed test. Now, before we look at the output of this in KNIME and do a working example, I want to introduce one more thing, and that's the Levine test. In statistics, it's an inferential statistic used to understand the equality of variances between the means of two groups. Some common statistical procedures like this t-test here assume the variances of populations are different. And what this test is going to help us do is understand if there is an equal or unequal variance. What it's going to do is it's going to test the null hypothesis that the population variances are equal. That's our null hypothesis. If the resulting p-test value is less than some statistically significant level we've chosen, typically 0.05, then the variances are unlikely to have occurred based on random sampling of the population of the variances. Thus, the null hypothesis is rejected. So in other words, if the p-variable is less than 0.05, then these population variances are not equal, and we can work under that assumption, and it'll help us choose which value to look at in KNIME. So let's take a look at how we're going to do an independent t-test using KNIME. So I'm going to take the output here of sample table that I've used something similar before, and I've got a column called row type, and I've got all my females and their ages, and then I've got all the males and their ages. And I want to do this test we've been using as our working example throughout this chapter. So I'm going to use the independent groups t-test node within KNIME, and I'm telling it to use the row type column, and I want to compare the averages of males and females with a 95% confidence interval against their age. And when I look at the output of the statistics, let's see what I've got. So I've got the average age of females is 46, the average age of males is 50, standard deviation, etc. Now, the Levine test that I've got here executing shows me, again, we're talking about what is the probability that these variances are, that the differences in variances are going to be caused by chance. Well, the p-value that it's come up with, based on degrees of freedom, we had 598 values in my sample, is 1.86 e to the negative 7th. This is well below the 0.05 threshold. which general safe assumption then would be that the variances are unequal. You don't obviously have to go with that choice, but that's what I would certainly believe. And in this case, I would say equal variances are not assumed to be true. In this case, we're doing a two-valued test to say that I assume these two ages were going to be equal, and this is by chance. Well, the p-value that I get here is 5.29 e to the negative 6. Again, well below the 0.05 threshold that I would have set that says that these two means are the same, which means I'm extremely confident at this point that the differences here is not sampling error or sampling differences that fell within the region of acceptance, that the average age of females and the average age of males are not the same. I can reject the null hypothesis. That's what I've learned from this test. So now let's do another one. This time let's do a paired t-test. And to start with, again, I've created a sample set of data. And this time when I look at the data, I've just got the two columns here. I've got your after score and your before score. Let's assume I've got a group of people who are taking a test. And this is their score before and their score after. So 2 became 35, and 20 became 414, and 5 became 48. And I want to say, basically, have their scores improved? So I'm going to go ahead and do a paired t-test against them. Now this time, I specify the left column, which will be their before score, and the right column, which will be their after score, and then I'm going to specify the confidence interval that I'm expecting to see. So I'll go ahead and execute this and open the view. And what do I see now? The before score, the average was 129, and the after score is 185. And my probability distribution, if I assumed that they had not really, that this test had not changed them in any way, and said they didn't learn anything out of the test, my p-value here is 0.04. And again, rounding up, using 0.0468 rounds to 0.05. It's like, ooh, I technically, I cannot discount the null hypothesis. I cannot reject it. But I am, we're very close. We're right on that threshold. And it puts us once again asking ourselves, what's the significance of getting something wrong versus getting something right? Assume, for example, this was PSAT scores versus SAT scores. And asking ourselves, did taking the pretest help you? Well, on the surface, you look at it and say it seems to have, but the probability is not terrible. Which side do I want to err on? Well, it doesn't hurt to take the PSAT, even if I'm not positive it helps them with their SAT scores. But it's worth, it seems to be, the risk of error seems okay that I would leave the test in place. That's how I'm going to do a paired t-test. Now there's one more thing I'd like to discuss in this chapter, and that's Cohen-D's kappa, the Cohen-D's D-score. It describes the effect size by expressing the observed mean differences in standard deviation units. And the standard deviation supplies a stable frame of reference that's not influenced by sample size, unlike those where standard error whose values increase or decrease. So the formula is actually quite simple. It's the difference between the means of the two data sets divided by the standard deviation. And the standard deviation in this case is obtained from the square root of the pooled variance estimate, which is in itself an entirely another calculation. And in fact, you can see it's actually a quite complex calculation based on the sample size and the degrees of freedom. Now, in the next few slides here, I'm going to show you an example of how to do this computation, but I'm not going to walk you through it. It's too detailed and unnecessary, again, with an understanding of 9. So I will show the slides, and if you want to follow along with that, just pause each slide in the video so you have a chance to actually look at it and follow along. Since 9 is computing the Cohen's kappa, the Cohen d-score for us, what we really want to understand is how to interpret it. It's a measurement of standard deviations, the difference essentially between these two data sets. So when you see a Cohen's d-score of 0, there is really no measurable difference between them. And as you see, that as the Cohen's d-score rises, the difference between the means becomes more and more pronounced, where you get all the way up to the working example of where the d-score is up to 3.0. There's very significant differences. Now, I'm not going to show you how to do this in 9 yet, because the way we're going to do this in 9 is actually part of a statistical model. And so I'm going to hold off showing you that until we start looking at decision trees, and we're going to use the scorer node to look at the Cohen's d-score and try to interpret it. So let's summarize what we've learnd. T-tests, we have simple sample method and for normal distribution. And we have 2 sample with equal variance, and we have 2 sample with unequal variance. And they both score and work, of course, slightly differently. And then finally we have our paired 2 sample, where we're looking at essentially before and afters. It's really the most important thing around it is sampling. Are the samples independent, or are the samples dependent on one another? That completes this chapter of the class. Feel free to move on to the next chapter.